Part 2 of net force, example 7, we have a 20 kilogram sign hanging from a pair of wires. It says the wires that will be used can withstand a force of tension up to 300 newtons. Determine the tension wire 1 and wire 2 and explain if you have any concerns. Okay, so here's a more advanced problem for net force. And what we're going to start with here is a free body diagram. Let's draw here's the sign, and there are three forces acting on the sign. As always, the most important one for this one is the force of gravity pulling it down. And then we have a force of a wire going this way. So that's tension, what do we call it here? Tension 2. And we have a wire going in this direction here, which we're going to call T1. So the force of tension 1, the force of tension 2, and the force of gravity, those are the three forces acting on the sign. And of course, we want the sign to be still. We don't want this sign to accelerate in any direction. Therefore, the net force, both horizontally and vertically in this problem, equals 0. Okay, once again, the sign, we don't want the sign accelerating up or down or left or right. So the net force in both directions is 0. That's a very important concept. Now, the next thing that's new for this problem is this down here. How do we calculate the force of gravity? The force of gravity is easy to calculate. We just use this formula here, which you're going to use a great deal in this unit and beyond. That is the force of gravity equals mass times acceleration due to gravity. The mass of the sign is 20 kilograms. The acceleration due to gravity, assuming we're doing this on Earth, is 9.81. So we multiply that together and we get 196.2 newtons. So that is the force of gravity on the sign. It is also the weight of the sign. So that sign weighs 196.2 newtons. Contrary to popular belief, when somebody asks you what your weight is, they're really asking you what your mass is, because your weight is the force of gravity acting on you. And your mass is just how many molecules your body is made up of. So when you say I'm 140 pounds or I'm 68 kilograms, you're actually giving them your mass, not your weight. Your weight will change if you go to Mars or the moon or another planet that doesn't have acceleration due to gravity of 9.81. Anyway, we'll get to more of that later. So now we found the force of gravity, or the weight of the sign, and it's 196.2 newtons. All right. Now we want to look at our two tensions. Tensions right here and right here. And you can see one of them is the tension 2 is completely horizontal. And the tension 1 is both horizontal and vertical because it's going up at an angle. So for tension 1, it has a horizontal component, or a vertical one as I've just drawn there. And I deliberately drew it there as opposed to over here. And it has a horizontal component. Okay, and as we said, the net force horizontally and vertically must equal 0. So just by looking at this free body diagram and the alterations we've made to it, you can see that this purple vector here going up, it must be this value here. Like, that makes sense, because if 196.2 newtons is pulling it down, then the vertical components of T1 must be pulling it up with an equal and opposite force. If it was pulling it with less force, the sign would be accelerating down. If it was pulling it with more force, the sign would be accelerating up. The sign is stationary, it is not accelerating. Therefore, this vector here must be 196.2 newtons. Okay, and once you've got that, that's the hardest part of the problem, actually. Once you've got that, then everything else just kind of falls into place quite magically. So let's just take this blue vector, T1, and separate it 40 degrees. Is it 40 degrees? Was it? Yep, 40 degrees up there. Right? We have a vertical component. we have a horizontal component, and now we know that the vertical component must be 196.2 newtons, and therefore it's easy for us to figure out what T1 is. We can just use trigonometry, and then we got the horizontal components also. So let's use trigonometry to find out T1, and we've got the opposite, and T1 is the hypotenuse. So we're just going to say that the sine of 40 degrees equals the opposite, 196.2, divided by the hypotenuse, which is T1, and therefore T1 equals 196.2 divided by the sine of 40, and that gives us 196.2 divided by the sine of 40, gives us 305 newtons. Okay, so there's T1. We've got T1 already. Great. Now let's go back up and find T2. And again, we're going to look at our free body diagram here and see if we can make some conclusions about what T2 should be. T2 is going completely horizontal. We said that the net force in both directions, horizontally and vertically, must be 0. Therefore, this T2, this green vector here, must be balanced by something going horizontally with the equal and opposite force. And just looking at the diagram, you can clearly see that it is going to be this vector. In other words, the horizontal component of T1 must be the same as T2, because they have to be equal and opposite so that the sign is not accelerating either to the left or to the right. And that's why I put an X right here, because you can see that that X is actually going to be the same as T2. And now we can again use trigonometry. Now we're talking about the adjacent, so we're going to use cosine. We're going to say cosine of 40 equals, actually, we're not going to say the cosine. Sorry, I'm in the back of the truck here. We're going to use the, you can use the cosine. You can use the cosine, but that assumes that you got this one correct. Oops, that assumes that you got this one correct. Let's assume, or let's not assume, but let's just not take a chance and pretend that you, and try and use information that's already given to us. So let's use the tangent. So once again, you can use the cosine. I'm going to use the tangent. The tangent of 40 degrees equals 196.2 over x, and x is the same as T2, and therefore x equals 196 divided by the tangent of 40. And let's see what that gives us. 196.2 divided by the tangent of 40 is 234 newtons. So that would be here, 234, and we know that's the same as T2, so we've just solved T2. There's your answer for T2. Here is your answer for T1. And if you want, you can check that with cosine. If I was using cosine to find out, I would have said that the cosine of 40 equals x over the hypotenuse over 305. So just go 305 times the cosine of 40. And what do you get? Exactly the same thing, 234. So you get the same answer either way, which is good. That's the answer to the question. But then you have to say, do you have any concerns? And the answer is, you're darn right you have concerns, because the wires are only made to withstand 300 newtons of force. And T2 is experiencing 305. In other words, that wire will not hold, it will snap, and the sign will fall. So yes, you do have concerns. Okay, and that's the end of that problem. Now we're going to do one more problem, but I'm going to do a separate video for it because it's a long problem. This would be your standard of excellence advanced question, which you should get some exposure to. So go on to lesson 22-3.